Hello, welcome back to What is Time Part 2 with P. Edward Swan. In the previous video, What is Time Part 1, we determined it is very difficult to synchronize any two clocks that are experiencing different environmental interactions. In Part 1, we imagined taking one clock on a journey around the solar system and leaving one clock back on planet Earth. Could we maintain the synchronization of these two clocks at every step of the journey? If we want to use Einstein's system of relativity to synchronize two or more clocks, we need to know all of the environmental interactions that each clock is experiencing. Therefore, we need to answer the following question. Is it possible to measure all the interactions that a clock can have with its environment? To answer this question, we must try to find the relationship between clock cycles, the tiny processing steps that make up each clock cycle, and the environmental interactions experienced by a clock. To understand the relationship between clock cycles, process steps, and environmental interactions, we will analyze the behavior of two identical light clocks. A light clock is special because it is easy to visualize its internal mechanisms. What is a light clock? A light clock is a box with a light pulse generator, a light detector, and a counter at the bottom side of the box, plus there is a mirror at the top side of the box. Also, the box has a vertical height that is 1 meter, shown as length L. To start the clock, we send the first light pulse straight up to the mirror, and the light pulse is reflected straight back, and when the light pulse is detected by the sensor, that counts as one clock cycle. The counter increments by 1, and the cycle starts all over again in a repeating loop. And that is all there is to understand the basic operation of a light clock. And now we will step through the basic operation of a light clock. To start, the generator sends a light pulse straight up to the mirror. It's reflected straight back down to the detector. A signal goes to the counter to increment by 1. A signal also goes back to the generator to start the process again. Another light pulse is sent back up to the mirror north, reflected straight back south, and that's 2 completed clock cycles. One more time, straight up north, straight back south, and we have 3 completed clock cycles. The only information that we receive from a light clock is the output, which only gives us the total number of completed cycles. And that is all there is to the basic operation of a light clock. The light pulse of a light clock is an electromagnetic wave. EM waves are complex objects that have many subparts that can be modeled with mathematical equations. An EM wave is a function of position and time, and it gives the electric and magnetic field strength at position x as it is changing over time t. Mathematics is just another information system that defines the relationships between groups of objects called sets of elements. Elements represent things like distance, time, and field strength. The equations for EM waves define regular and cyclical mechanical behaviors. The light pulse is just a sub-mechanism of the light clock machine. Every clock is a machine with moving parts that are influenced by environmental factors. Clocks are not special. They are just machines. To define the relationship between clock cycles, process steps, and environmental interactions, we will use the principles of information systems to analyze two light clocks of identical construction. Information systems work by breaking a problem down into little pieces, organizing the little pieces into functional groups, and then calculating the relationships between these constructs. Therefore, the first step is to break down the operation of a light clock into a series of little pieces called processing steps. But to accomplish this, we need to create a simple definition of motion that is made of discrete processing steps, the tiniest little subticks and subtalks of a clock. And here the idea is that we can see the clock cycles that come from a clock. 1 clock cycle, 2 clock cycles, we can count those. That's what the output is from a clock. But within each clock cycle, there's a whole bunch of subcycles, little processes that happen to create a tick, little processes that happen to create another talk. And within each subcycle, there's sub-subcycles, all the way down into some discrete subcycles that can't be broken down anymore. And there's a whole bunch of those processes that go into each subcycle, and subcycles go into clock cycles. And that's how it's all broken down. But we can't see all the stuff that's happening underneath. And science says we can count the number of cycles of a clock, and we have electromagnetic radiation, that's the light pulse in the clock, And then underneath that, we have quantization, which are the little particles and pieces that make up electromagnetic radiation. And then beyond that, nobody really knows if there's sub-quantization. And then on top of all that, we've got velocity, gravity, heat, and other environmental factors that are influencing the clock system as well. And so when we're dealing with clocks, we have to take into account all of those factors. Motion is the change in the position of an object over time. Imagine that you are a door-to-door salesperson and you are visiting all the houses on a block. You would move from one position to the next position by taking one step at a time. The longer the block, the greater the number of houses and the more steps you would have to take to visit all the houses on the block. If we count the number of steps that we take, this gives us a definition of distance such that more steps equals more distance and less steps equals less distance. Now we have an information systems model of motion that provides a very simple relationship between distance and motion. In this example, we can also notice that the total number of steps for each salesperson to travel to the end of the block is different. The blue salesperson has to take more steps because the right side of the street has a different configuration with different sub-processes than the left side. Nevertheless, in both cases, the distance traveled is equal to the number of steps that are required to complete the journey. And there's one more point that we need to understand when we look at this slide. We can measure the distance that the blue side travels or the green side travels, and we might take a measurement and we might see, oh, it's 54 steps with that direct measurement. And the same thing on the blue side, it's 54 steps. If we have two identical clocks, two identical systems, the street seems to be the exact same distance from the start of the block to the end of the block. Start of the block to the end of the block. We can measure those directly, and these things seem to be identical. But there's a lot of indirect sub-processes that we can't see directly. So when we're dealing with complex systems like a clock, there's a lot of sub-processes that have to be understood indirectly. When we take into account all of the sub-processes, we have 84 steps with sub-process on the green side and 108 steps with sub-process on the blue side, which makes those systems different, even though they may seem to be the same when we measure them directly. And so we have to take all of that into account when we're dealing with these complex systems that we call clocks. Here we should take a moment to stop and acknowledge that mathematics is just another type of information processing system. Mathematics is not special or conclusive. Like any information processing system, it has strengths and weaknesses. Mathematics is really good for counting and tracking the relationships between collections of discrete objects called elements. Elements can be associated to any real-world objects, and then mathematics can be used to estimate the relationships between those objects as they are accumulated into various sets. In the case of motion, the set of objects we are trying to estimate is the set of process steps necessary to cause motion over a distance. Natural language is another type of information processing system. We're going to use natural language as the basis for our simple model of motion. A natural language model is easier for humans to understand and will help us to think creatively. The important point is, no matter what information systems model we decide to use, mathematics or otherwise, the relationship between motion, the changes in position of an object, and distance is fundamentally the same. More motion equals more distance, and less motion equals less distance. And it is true that mathematical formulas are not special. For instance, if we take some formula, y equals 2x, it just describes a relationship between the elements of x and some elements of y. For every x, we get out 2y. We can say the same thing in natural language. We can say that y equals distance and x equals motion particles, and we can describe that relationship. The distance equals motion particles at a ratio of 2 to 1. Those two different information system models are functionally equivalent. And here we could use a programming language. We have two variables, inputs, and in this case we'll just call them strings. We have distance and motion particles. Then we can describe a relationship with a method call called move distance, and it takes in some motion particles, and it produces an output called distance, which just takes motion particles and puts it together with another motion particles. So you get two motion particles put together, and you return that. Then when you actually run it, here we define motion particles as the string pop, and we run this move distance, which is this method call, and it returns the output pop pop, because it just takes pop and doubles it up. Functionally equivalent. All these are functionally equivalent. This programming language just happens to control an actual physical system on a microchip, controlling all of the little electronic impulses and switches to actually make it happen, but all of these are functionally equivalent. Mathematical formulas are not a special type of information processing system that is special or more authoritative than any other information processing system. We need to use common sense and reasoning to continue making progress in science. We cannot stop questioning the assumptions made by those great minds of yesterday that produced the miracles of technology that we have today. So now we are going to use a generalized information systems approach to build our models. An information system's definition of motion requires that the changes in position to cover a distance must be constructed from a set of distinct and countable processes. Therefore, we need a set of basic instructions that represent one process of motion, one discrete motion step. To simplify our model, we will just use 4 process steps called one step north, one step south, one step east, and one step west. The different arrows will represent the associated steps. Now we have a basic set of tools to describe a clock cycle. To begin, we will explore the case where 2 light clocks, clock A and clock B, are at rest, and they are adjacent to each other. We can deconstruct a clock cycle into a set of information processing steps, a set of instructions. To create a simple model, we will define one clock cycle as 20 motion steps, 10 steps each way, to move a distance of 2 meters, 1 meter each way. Of course, the actual number of processing steps is very large, at least the Planck number, which is approximately 10 to the 35 parts per meter, or approximately 10 to the 44 parts per second. There are a lot of little processes that happen to create movement, but they are just too small to measure directly. Okay, so now we're going to step through the process as the 2 clocks complete one cycle. The light pulse travels north in little incremental steps until it turns around. And here we should notice that the light pulse is at least partially redefined when it reflects off the mirror. The direction of the light pulse is now in the south direction instead of the north direction. If the mirror was not there and there was no interaction, the light pulse would just keep going north. Information is exchanged when there is an interaction between 2 things. As far as I know, interferometer experiments do not account for these types of interactions, but they should. And now the light pulse is moving in the south direction after it is reflected off the mirror, and we have 10 more process steps until, finally, each clock has completed one cycle, 10 steps north and 10 steps south, and the counters have both incremented by 1. Now we can make a list of all the process steps for each of the light clocks and compare them. The list of process steps is identical for both light clocks, and both clocks will always count the same number of clock cycles. In other words, the clocks are synchronized. Identical clocks that experience the same environmental interactions should be expected to remain synchronized. This is the easy case. And we can see on the chart that there's, out of 20 steps, these 20 steps are exactly equal for both of these clocks. The difference in the number of steps is always 0 because they're each counting the same number of steps, and the difference in the cycles is always 0. Whenever one clock changes, the other clock changes to a completed cycle. And we count one completed cycle here, and if the list kept going, it would be eventually 2, 3, 4, counting the cycles, and they would always be the same. Now we will add just one environmental interaction to clock A and repeat the example one more time. We will accelerate light clock A to 10% of the speed of light in the east direction. Light clock B will remain at rest. Clock A is now moving at a velocity that is 10% of the speed of light. As clock A passes by light clock B, the 2 light clocks will synchronize by resetting their counters to 0, and then we start the clocks. Both clocks start out the same, but they will soon show a difference. And now we will step through the processes for both of the light clocks. The light pulse is now moving in the north direction until we get to the first difference. The acceleration of light clock A is caused by an interaction with some object in the environment, and it causes the exchange of information between light clock A and that object. Light clock A is now moving one step east for every 10 steps that light pulse A is moving either north or south. And here we see that it has an extra set of instructions here, just one step east. And clock B doesn't have that. And so now we continue the rest of this one process north, and we had 10 steps north and one step east. Clock B just had 10 steps north, and now it's already turned around. Now we will continue on to the second half of the clock cycle. The light pulse turns around and is moving in the south direction until we get to the second difference. We know that the acceleration changes the fundamental nature of light clock A because the information, the list of process steps, that is required to describe the behavior of light clock A is not the same as it was before it was accelerated. We can see that light clock A has an extra step, one step east, because it's moving in the east direction at 10% of the speed of light. Light clock B does not have that processing step because it is at rest. And that's what makes the difference between these two clocks. We can continue until light clock B has now completed one cycle, a tick or a tock that we can measure, and light clock A has 2 more steps to process before it will complete one cycle. Over time, light clock A is recording less clock cycles than light clock B. And the two light clocks continue to process until finally, light clock A has completed one cycle, a tick or a tock that we can measure, and light clock B is 2 process steps into cycle number 2. Until there is a change in the system, light clock A will continue to record less clock cycles than light clock B. Now we can make a new list of all the process steps for both of the light clocks and compare them again. We can see that the number of process steps needed to complete one cycle for light clock A is greater than the number of process steps needed to complete one cycle for light clock B. Light clock A is recording less clock cycles than light clock B. The counters on the light clocks only increment at the completion of a cycle. So based only on the clock cycles, the counter for light clock A will record less time than the counter for light clock B. And if we take a look at the chart, we have light clock A and light clock B, and we have all the steps for light clock A and all the steps for light clock B. And what's important to notice at this point is that it takes light clock B 20 steps to complete one clock cycle, and it takes light clock A 22 steps to complete one clock cycle. Light clock A is running slow compared to light clock B. And we see that there's a difference in the number of cycles produced by light clock A and light clock B, and this difference will accumulate over time. Now we have examined the relationship between clock cycles, process steps, and environmental interactions. Environmental interactions can increase or decrease the information in a system. When a system is injected with additional information particles, it forces the system to process more information. When a system processes more information, the cycles of that system will generally be elongated. If we plot the changes in the instructions as the clock is accelerated, we would expect a linear curve like the red curve in the graph. The actual change in the clock cycles caused by a change in motion is given by the Lorentz factor. And here's the formula for the Lorentz factor, where v is the velocity caused by some acceleration of the clock, and c is the speed of light. If we compare the list of processes given by our simple information systems model and the actual change in the behavior of light clock A, the results are similar as seen in the graph. More instructions equate to longer clock cycles in both cases. However, complex systems generally do not produce linear outputs. Based on the principles of information systems, it must be the case that the additional information is processed in parallel at first and then it gradually becomes necessary to be processed in serial as the information density of the system increases. And here we see the two curves. We see the Lorenz factor curve, which is the blue line, and we see the curve from our simple information systems model, which is the red line. And in both cases, the more acceleration, and here's 100% of the speed of light, and here's 0% of the speed of light, as the velocity of the system increases, in both cases, the clock cycles decrease. The simple model, the red line, predicts that it would be 2 to 1 by the time you reach 100% the speed of light. The Lorenz factor says by the time you reach 100% of the speed of light, it's off the charts. But at the beginning of the curve, there's hardly any change at all. 10% of the speed of light, 20% of the speed of light, 30% of the speed of light, it only changes a little tiny bit. It predicts a change of 1/2 of 1% at 10% of the speed of light, whereas the information systems model predicts about a 10% change at 10% of the speed of light. So it's not a one-to-one situation. The actual curve that explains the changes in the behavior of the clock system predicts a more complex system than just extra instructions being processed. They have to be processed in parallel. That's what it suggests. Complex systems display behaviors that are resilient to change at first and then become overwhelmed at some point. To illustrate this idea, we will go back to the door-to-door salespeople. This time, we will have a team of 3 salespeople on each side of the street to represent parallel processing. We will step through the journey 5 steps at a time. And now we will step through the journey. We see that the teams are processing their side of the street, and then people are splitting off to do the little sub-processes. We keep going. We see the second set of people splitting off doing the sub-processes. And then the teams keep going, and then eventually they come back together at the very end. Finally, at the end of the route, the blue team is only 8 steps behind the green team, even though the total extra distance the blue team must cover is 24 steps greater than the green team. Parallel processing is just one possible mechanism that complex systems might use to process additional information, resulting in a non-linear curve. Complex systems such as a clock or a sales route are resilient and efficient when close to their normal operating range. But as the system becomes overloaded with new information, such as energy or motion particles in the clock example, or more customers in large apartment complexes in the door-to-door example, the output of the system will show profound changes. Can you imagine if the sales team on the blue side of the street had gigantic apartment complexes that they would have to navigate? They would need a whole nother plan. It wouldn't work the same way. They couldn't just drop people off on this at the beginning of the street and then expect that the blue team would be able to achieve the objectives. The green team would still have very simple objectives to achieve, but the blue team would have a gigantic apartment complexes. They would need breaks, maps, planning. People would get lost, tired. It would be very, very difficult, and things on the blue side would just slow down to a stop, basically. Just like heating a pot of water, you can heat it up to a certain point, but then it will begin to boil, and any additional heat will be lost by evaporation. The system cannot contain more information in the normal configuration. It must change formats. We can look at the Lorenz factor chart again and analyze the curve. The curve shows the system is processing information in parallel at the beginning of the curve where the system has extra capacity. However, at the point where the two curves diverge, there is a phase change or critical mass threshold where the system is overloaded, causing extreme elongation of the clock cycles. If we look at these two curves, they're very similar all the way up until about 90% of the speed of light. And the red curve, of course, is the information systems model, and the blue curve is the Lorenz model given by this formula here, the Lorenz factor. We have a normal operating range for mechanical objects such as a clock or an elementary particle. Information is being processed efficiently, causing only small changes over this range from about 0 to 90% of the speed of light. But there's an extreme environment outside of the normal operating range of the object, which causes extreme elongation of the operating cycles, right? The clock cycles of any object become extremely elongated as you approach the speed of light. Of course, we're only interested in some part of the curve around 10% of the speed of light for our tests, and our experiences are all really close to this lower end of the curve here, though some elementary particles have been accelerated in particle accelerators and seem to agree with this Lorentz curve, so they would probably be overloaded as well. In any case, there is a relationship between the information that forms a complex system and the various system outputs that we can measure. For our purposes, we are interested in the relationship between the information in a clock system related to motion and the number of clock cycles of that system. In the figure, this light clock is moving at 10% of the speed of light, and the clock cycles are elongated by 1.005 times. And here's a blur motion chart that shows a light clock moving at 10% of the speed of light to the east. And you see it has three positions where the mirror is moving, and generally the depiction is that the light is moving at an angle, reflecting off the mirror, moving at an angle back, and hitting the detector and completing the cycle. But that's an averaging system, and it may be useful for certain calculations, but what we're trying to show right now is that the information that the light ray is moving in the north direction and back down in the south direction, that's the same. The light clock still has to do those two functions. When the clock is in motion, there is some additional information here, and that additional information causes an elongation of the clock cycles. This system has to process that additional information, and more information equals longer clock cycles, and moving clocks run slow. In this figure, the clock has increased its velocity to 50% of the speed of light, and the clock cycles are even more elongated with a value of 1.1547 times. The only change in the system is the information related to motion in the east direction. The velocity in the east direction has increased. Based on the principles of information systems, it must be the case that a moving clock runs slow because the information contained inside the system has changed. Now that the velocity of the clock is at 50% of the speed of light, we can see that the number of instructions that it has to process has increased. For every light pulse that travels in the north direction, 50% more instructions are needed to create the movement in the east direction. And then we have 50% more instructions in the east direction for the clock when the light pulse is moving in the south direction. There are extra instructions in the clock based on information systems, and that's what accounts for the difference in the clock cycles. The clock at rest only has to produce a light pulse that moves straight up north and then straight back south. The clock in motion has to do additional processes, additional steps, and that creates an elongation of the clock cycles. The clock moving at 50% of the speed of light has 1.1547 elongation of the clock cycles compared to the clock at rest, which is 1.0. In every case, moving clocks run slow because they must process more information per clock cycle, and therefore each clock cycle is elongated. Moving clocks produce a smaller number of elongated clock cycles compared to a clock at rest. A clock is just a machine with a set of instructions. A change in velocity equals a change in the operating instructions of the machine. The new instructions can be detected indirectly when we measure the changes in the output of the system. Please see the link below and join me for What is Time Part 3, where we will continue to work on the difficulties we face when we try to synchronize multiple clocks. At this point, we only need to understand there is a relationship between clock cycles and velocity, energy, motion, information particles, such that moving clocks run slow. In the next part, we will use this relationship to detect and adjust for environmental interactions. Thank you for watching, and please like this video, share this video, and subscribe to this channel. In my book, Darwin's Machines, you will find a variety of fascinating topics such as time, space, the Big Bang, and free will. If you like science, you will love Darwin's Machines, an information systems approach to understanding the natural world. Please see the links below where you can purchase my book. Also, I am currently working on human longevity technologies so we can all live longer and better lives. Over the last 20 years, I have developed a groundbreaking design for biomedical sensors that will revolutionize the $200 billion per year medical devices market. If you would like to help me bring this product to market, please contact me by email, or you can also support my work by purchasing my books. I am looking for people with all kinds of backgrounds to help me with every aspect of the project, including the technical, organizational, funding, networking, and everything in between. Thank you for your support, and be well.